Hello. Um, we're gonna wait a little bit, but if you want, you can start off with the first question. It's always good to start off with a Taylor series question, um, with interval of convergence, because that's always such a big question. So I'm gonna write that down, and then we can start. So if you want tomatoes, if that's your name, you can find the Taylor series, the interval of convergence of this. Find the interval of convergence. Remember that this is usually, if it's on a free response question, it's usually the first free response question. So we're using this of, let's do this sum right here. Also remember that the important thing is the general term. We'll keep it simple for now as a way to sort of get warmed up, and it's radius convergence, so it's a little bit annoying. We're gonna find this one. So you can start this if you want. I don't know if you're here still, but I don't know if it's just you too. Okay. Um, you seem like a nice person, so you can get started with this. It is, again, one of the most important skills. One thing is that as you're doing this, just do the process. Even if you don't do it successfully, just doing the process is important. I'm going to start the process in a couple, and maybe like 5 seconds or so. But interval of convergence, again, is usually part A. The big thing is that if they give you a series like this sum thing, as well as the terms, just remember that when you're doing this, you're always doing it on the general term. So when we're about to do interval of convergence and all the ratio test stuff, I'm going to do it on this formula right here. So just be wary of that. So I'm going to just start because it's an interval of convergence time. So let's do this. So remember what you do is you set up the ratio test. And when I'm doing this ratio test, I'm going to be very precise. I'm going to do all the stuff. So I'm going to do all the absolute value stuff as well. And then what you do is remember is you plug in n plus 1. So anytime you have this n here, you're going to plug in n plus 1 instead. So I'm going to replace n plus 1 because this is what the ratio test says to do. And we don't sort of break our series rules. So again, anytime I have an n, I replaced it with n plus 1. Now what I do is I flip this general term. So I'm going to flip the general term. That's my favorite part of the ratio test. Actually, my favorite part is right now is when you start canceling all the stuff out. So I'm going to close my absolute value bars, and now I'm going to cancel stuff out. So the easiest thing to cancel out, if you're sort of familiar with this, is any negatives, but we don't have any negatives here. And we would cancel out the negatives because of the absolute value. And then we need to cancel out these n's. And end stuff is also not hard to cancel out because you're always doing same heavy. So we're basically just going to ignore them because n squared over n plus 1 squared will be 1 as n goes to infinity. So now we just need to focus on the numbers. Well, if you have like 3 to the 10th over 3 to the 9th, you'll just have 1 3 remain. And so that's going to be the case in this as well. And then the 3's act like the x's. So you're also going to be left with an x. I always leave my x in absolute value because we don't know what the number is. You don't actually have to have the 3 in the absolute value because absolute value of 3 is obviously 3. But I have my x in the absolute value. And remember what you always do is you always say that this is less than 1. So I'm going to say that this is less than 1. And then I isolate this. So I'm going to isolate my center. Here I'm dealing with the Maclaurin series because it's x minus 0 technically. So it's going to be less than 1. And then I'm going to bring over the 3, so it'll be 1/3. And if they were asking the radius convergence, this would be the radius convergence. So this is the radius. And sometimes they just ask that, but in this case, we're going to keep going. We're going to do the full interval. And just remember that on the AP exam and on maybe college exams as well, just doing this part right here gives you the majority of the points. And now we're going to do the hard step, but again, the hard step is not super important in terms of getting it right. But what you do is you let the limit as x, not the limit. You first, I like to draw this picture. Some teachers don't teach this, but the center point is 0 because it's a Maclaurin series. And then you add 1/3 to the radius, and then you subtract 1/3 to find the endpoints. And to finish off the question, we have to test whether it converges or diverges at the endpoints because we know it converges within the radius convergence, and we don't know, and we know it converges diverges outside of the radius convergence. So we only care about the endpoints. And what we're going to do is we're going to take each of these endpoints and we're going to plug it into our x's here. So just be careful. There's a lot of variables, but we're plugging into x. So I'm going to do that right now. I don't know why I'm writing limit. I'm just going to write x equals negative 1/3, and x is equal to 1/3. I like to plug in the 1/3 first because plugging in the positive number is just so much easier because there's less negatives. So I'm going to plug in 1/3 first. And again, I'm plugging it in right here. So notice when you do this, all these 3's cancel out. So you're just left with this series. And I don't know if you know this, tomatoes, but this is the most famous series in the world. This is the the harmonic series, so it diverges. So this is harmonic and it diverges. Unfortunately, the negative 1/3 will be a little bit more annoying, so I'm going to do that more slowly. Again, I'm going to take the general term and I'm just plugging in negative 1/3. Oh, you're right, Smelinor. It is n squared. So this is a p series, there's p equal 2, which is greater than 1, so this converges. Because it's harmonic. Good catch. We basically, every single Taylor series question, if you're doing a multiple choice, is fricks. Like, this isn't a potential frick question. This could be like 5 of the 9 points of one of the big fricks. This is how I categorize the Taylor series fricks, where one of them you have to do interval of convergence, and this is the one where we're doing interval of convergence for. Okay, so for this one, let me try to redeem myself in your eyes. Yeah, but even if you see the words interval of convergence, you just start doing this process. And it's usually part A of these fricks. Anytime I have negative 1/3, I'm going to break it up into a negative 1 to the n times 1/3 to the 3 to the n. One of the things is that we've done a lot of fricks before, so I just don't have a lot of fricks. That's my problem. And then when you cancel these out, notice you'll have this. And this is an alternating harmonic series. Not harmonic series. I keep saying harmonic series. It's an alternating p series in this case because it's 2. So this converges as well. So this converges. So the final answer, if you don't know, is negative 1/3 and 1/3. With brackets on each side, because they converge on both sides, because one of them was harmonic and one of them was alternating harmonic. Hopefully that makes sense. But this is the most classic example of interval convergence. I was just, again, going to do multiple choice questions that could appear in fricks, and usually the wording is pretty similar, like finding general terms, things like that. So I was going to maybe do one more of these, what is it called? Interval convergence. So I think hopefully this made sense. Good job, Tomato, on catching that mistake. It is n squared, and that affects the convergence and stuff. But again, even if you like get up to this point and you like plug in the endpoints, you'll get the majority of the points. I'm gonna move on though. We're gonna do interval convergence again. So again, like I don't know what your name is, but it looks like it's Amelia Shapiro or something. When you're finding the interval of convergence, they usually just say find the interval of convergence or find the radius of convergence. So there's not really ambiguity in the wording there. And it's usually part A, especially if they give you the general term. It might be part B if you find the general term in part A, but in this case, it will be the general term. So let's practice one again. Let's do one with negatives. So negative 2 to the n times x minus 1. So here we're not dealing with the Maclaurin series. Here it will be like x is equal to 1 will be the center point. And that would be like in the wording of the frick. And then we're going to divide it by n this time. So if you want, you can set up the ratio test and start doing it as I get a drink of water here. I just think this one it's very important because it doesn't just appear on interval of conversion fricks for Taylor series. It also appears in just random times that they'll just ask you to do either the radius or the interval given it. So I'm going to get started. It doesn't really matter what the n is, but we'll go right here. So remember what you do is you write the limit, not the limit, set up that absolute value bar, plug in n plus 1. So we're plugging in n plus 1. We're not bumping up everything by n plus 1, but in this case, we are plugging in n plus 1. So we're doing that. And then we're flipping everything. So I'm going to flip everything. So I'm flipping everything, and I'm going to set up this, doing these shorter cancellation things. So remember that the ends are the easiest part to cancel because it's same heavy is what we call it. So as the limit goes in n goes to infinity, n over n plus 1 will be basically the same thing. So these will just cancel. Next, we have the negative 2's to deal with, but it looks like we'll have one more negative 2 on the top. And also just be careful, we don't actually have -2 on the top, we have just 2 on the top because everything is with an absolute value. So we're just gonna be left with 2 here. I'll write this on the next line. And then the x minus 1s are treated like the 2s, the -2s, where you have 1 more on the top, so when they cancel, you'll just have x minus 1. These are absolute value bars. This is the number 1, of course. So one thing that people mess up when they're starting doing this is that they'll distribute the 2, but we're always trying to isolate the center point. So we always do less than 1 because that's where the ratio test says things converge, and we just bring over the 2. So it's x minus 1 is less than 1/2. This allows us to draw our little picture here, so let's do that. Center point is 1 again, and then you add 1/2 and subtract 1/2. I think that's going to be 3 halves and then 2 halves then, or 1/2, sorry. Add 1/2, subtract 1/2. Now for the fun part, or the most annoying part, plugging them in. Again, don't be too crazy. Don't feel, when you're doing this, don't get too scared, like, oh my gosh, this is so hard. Because again, just doing most of this will give you 4 of the 5 points. This is really, all of this work that I'm about to do is really 1 of the 5 points when you're doing on an AP exam. So I'm gonna plug in 1/2 here. Again, you plug it in for x. So let's do that real quick. Not for n. -2n times 1/2 minus 1 is -1/2, I believe, right? So that would be -1/2. Am I doing this right? I think I am. Yeah. Over n. Do we have to write the sum thing to get credit? I mean, technically, you have to write the sum to get, because we're checking the series and not the term. So I write the sum. I'm not sure if they would count off if you didn't write the sum here, but I'm just going to be careful and write it. Anytime you have this negative number business, you always try to break it up. So it's like -1 to the n times 2 to the n. Same thing with the -1/2. It's -1 to the n times 1/2 to the n. So here I'm going crazy. I'm doing the left side first, even though that's harder because of these negatives. Hopefully you see that 2 to the n and 1/2 over n will cancel out because you'll have like 2 to the n divided by 2 to the n. So these will just cancel. And then I like to try to combine my -1s. That's the entire purpose of me splitting up the -1s. So it'll be -1 to the 2n. That's an ACT rule or an exponent rule, where -1 to the n times -1 to the n. If you have the same base, you add the exponents. Then you divide by n. -1 to the 2n, this is when you have to decide whether this is still alternating, always 1 or always -1. But -1 to the 2n is always positive, or it's always even, sorry. So that's going to be 1. So this is going to end up with 1 over n. And this time, tomato, I believe that this is the harmonic series. So this does diverge. No, you don't multiply the bases. It's like when you have like 3 to the 4th times 3 to the 5th, it's 3 to the 9th because you add them up. So it's like -1 to the n times -1 to the n. No, that's not how exponents work. Like, yeah, so like notice over here, I'm not multiplying the 3's. I'm just like doing -1 to the n times, it's like -1 to the n plus 1, n plus n. But this diverges. When you plug in 3 halves, you get, we're going to plug it into the general, so it's over here on the top. 3 halves minus 1 is 2. And then again, what we do is we are going to split up this -2. Like so. And here it's the same thing. The 2 to the n times 2 to the n, these two, the bases don't multiply. It's this exponent rule. How do I have 2 to the n? It should be 1/2 to the n. Sorry about that. This is getting a little sloppy. But it's 1/2 because when you plug in 3 halves, it's 3 halves minus 1, so it's 1/2 to the n. Yeah, I caught my mistake before you did, tomato. These do cancel out. And how did I notice that I made a mistake? It's because when you do this, always it cancels out. Most of the time, I'm gonna make up a stat here, but like 80% of the time, you end up with either a p series or an alternating p series. So it's like a little bit weird that it was 2 to the n times 2 to the n and they didn't cancel. Usually the numbers cancel nicely. I'm just being very careful with the negatives so that when they cancel, I still know what's going on with the negatives. But usually it just like cancels out and it'll be like nice and easy like this. Or you might not even have a p series, it might just be like -1. So this one is alternating harmonic, so this one converges by AST if you want. I think you could just say alternating harmonic too. Again, all this work is like so much work for 1 point. 1/2, 3/2. They converge on the right side and diverge on the left side. So this is the answer. So hopefully this makes sense. Again, it's like annoying, but just knowing the process is pretty helpful. Doing the ratio test is much more important than these small little tests at the end. And I think most people can do the ratio test, canceling out the ends, canceling out the x's, canceling out the numbers. Be careful with the negatives. And also, if they ask radius, just like stop here, don't do extra stuff. But I think that's good for interval of convergence. It's already been over almost 20 minutes. But it is important because it is bulks of questions. I'm going to start doing questions that are more Taylor series-y, where you like are given derivatives and stuff. So let's do those. I'm going to start off with a couple multiple choice questions, and then we can do some harder ones. So like, for example, like a very common question is like on multiple choice, like you're given the second derivative or something. Is like x squared plus 3x plus 1 or something. And then you're asked the coefficient of the x to the third term. Yeah, this is what I want. About x equals 0, so it's Maclaurin. We can practice one without being Maclaurin if you want to practice as well. So like, for example, like f triple prime of x is equal to, I don't know. I don't want to go too crazy. Let's do sine of pi x. I think this works. And then we're finding the coefficient of, these are two questions, by the way, of the fourth term. And the Taylor series, or just abbreviate TS, about x equals 1. Again, pretty classic multiple choice questions. Okay. And basically, this is just testing the relationship between the factorial formula as well as the Taylor series formula and derivatives. So I'm going to start off with this first one right here. So what you do is I just always write out the coefficient of the x to the third term in general, which is going to be f triple prime of 0 over 3 factorial x to the third. And then I'm trying to find the entire coefficient. So keep in mind, this will be the entire coefficient, the derivative at 0 divided by the factorial. So what I have to do is I have to take the derivative. This derivative is pretty easy. It'll be 2x plus 3. But just remember that you should have no x's in your coefficient, so we still need to plug in 0. We're going to plug in 0. And of course, that is going to be 3, because 2 times 0 plus 3. So we're going to be left with 3. But if you're doing multiple choice, 3 will always be an answer choice, but that's not the correct answer because we still have to divide by the factorial. And really, you don't have to simplify here, but 3 over 6 is 1/2, so the answer is 1/2. We're doing Taylor series. Always fun. Okay, so this is the next one, sine of pi x. So again, usually the one they want you to find is the next one. Maybe if they're going crazy, they will actually define 2 more, but how crazy can that be? But what's the x to the fourth term? It's going to be x minus 1 to the fourth, of course. Fourth derivative, so we have so many derivatives that we can't use tick marks anymore. And just remember that we still have to divide by 4 factorial. So now we're going to take a derivative because we're given the third derivative. I mean, just be careful with chain rule, of course. So the derivative is cosine of pi x times pi. Remember, you still have to plug in the number. So this is actually wrong. There should be 1 here because it's whatever the center point is. So notice I have x minus 1. Over here it was 0 because my center point was 0. It was a Maclaurin series. But over here it's going to be 1. So I'm going to plug in 1. And I think I get cosine of pi times pi. Knowing trig is obviously nice. Cosine of pi comes up very often, so it's -1. And then I'm done because I just put this number right here. And that's that. Pretty common examples of multiple choice questions. I don't think anybody has a question, or if you do, let me know. But we're going to keep on doing these sort of simple multiple choice questions that have no multiple choice answers. Okay, so this is sort of backwards. A lot of times they'll give you a Taylor series, for example, like this. Like say you found this in part A. So this could be a frick, as somebody who asked, like, why aren't we just doing fricks? But sometimes they just ask these sort of questions where they'll like give you a Taylor series. So you might have found this in part A, for example, and part B would be like find a certain thing. And what we're trying to do is we're trying to find so this is Maclaurin because notice it's x and not like x minus 2. But we're going to find the fifth derivative of this function, if this is the Taylor series. So this is backwards. This is instead of being given a derivative and trying to construct the Taylor series, here's the Taylor series. Now try to find a derivative. Again, this is most likely to be on multiple choice, but it could be on free response questions, like a small part B or small part C or something, after you find the full Taylor series in part A. So what you do is you locate the correct term to use, and notice that on this question, it's going to be this guy right here, because I have x to the fifth, and the fifth term involves the fifth derivative, because the fifth derivative, 5 factorial, x to the fifth, all match. So let's write that down. I always just keep writing the formula over and over and over and over again. Fifth derivative, 5 factorial, exponent. You know, they all match. And then in this specific example, this is 3x to the fifth. Just be careful and include any negatives if there were negatives, but here there wasn't a negative. And now I just isolate the fifth derivative. The x to the fifths cancel. Some people just only write the coefficients. And so it looks like to finish this off, this answer, I just have to bring over the 5 factorial. I know 5 factorial off the top of my head, it's 120, so I'm just going to write it. I don't know if you need to simplify, to be honest, but it's 360. So another pretty common Taylor series question. But if you're good with that, we can go slightly harder. So let's go a little harder. Let's do the factorial formulas. So this one, I again forgot your name. I think it's Amelia Shapiro or something. You asked to do fricks, and like the next question would be multiple choicey, but also it would be like the first part of a frick. And remember that Taylor series fricks appear in 3 varieties. One of them is the one we did or practiced earlier, which is you do interval of convergence for a lot of the question. And then for one of them, you're going to be given a derivative formula. So for example, in this case, I have this derivative formula. So when I see the Fn thing, even if it has a lot of words, I know that this is the question where I have to do the derivative formula thing. I'm just going to copy it off one of my homeworks. Sometimes they'll say like f of 0 equals 1 as well, even though, because some people don't know 0 factorial. Okay, so sometimes you're like given this derivative formula. So a huge question you're asking yourself in every single Taylor series question is, do I use this factorial formula in order to create a Taylor series, or do I just go from one Taylor series to the next? And when you have this formula of the derivatives, Fn, I just know that I have to create the first Taylor series. I don't have a Taylor series already on the page. I might work with it later and like take a derivative, for example, of that answer, but I need to create the first Taylor series. And how I do that is using the formula. They also didn't say which one, so we're going to do the first third degree. Remember that third degree, again, doesn't mean the first 3 terms. That means up to the x cubed term or x minus 1 cubed term. So anytime I do these questions, I start off with the Taylor series. So it's going to be f of 1 plus f prime of 1 over 1 factorial x minus 1. So this is just me memorizing the formula or just knowing the formula. I haven't really thought about the question other than the fact that, sorry, there should be f of 1 equals 0. I can't even read my own notes. Is that right? Because yeah, if you plug in 0 for n, you would get 0 because it'd be 0 over 1. Okay, so again, I'm writing out my Taylor series. So I'm writing it out. It's centered around 1, so we should write that down. That'd be part of the wording. So this is my Taylor series right here. And again, I go up to this term because this is the x to the third term. Then I start plugging in the derivatives into this formula because this tells me how to find the numerators of these coefficients. F of 1 is 0, as they said. And then I remember that you're not plugging in the center point, you're plugging in the derivative. So for this term, I'm going to plug in 1 because it's the first derivative. For this term, I'm going to plug in 2 because it's the second derivative. And then I'm going to plug in 3 for this one. So when I plug in 1, negative 1 to the 1, that's the alternating part. So I just know that it alternates between positive and negative 1 to the 1 is negative. So this will be the first negative 1. And I think if you plug in 1 to all this, you're just going to get f prime of 1 is negative 1. So I'm going to replace f prime with negative 1. But I still divide by the factorial. Hopefully that makes sense. Let's do it for 2. Well, you can do it for this one, this first thing, but again, it's alternating, so this will just be positive. And then if I plug in 2 here, if I'm careful, check my work, but I think I get 2 squared over 2, which simplifies to be 2, just for the second derivative though, and I divide by 2 factorial though. And then I'm going to do the last one. I'm going to plug in 3, so I actually know that it will be negative. And then 2 cubed is, what is 2 cubed? No, we're not doing 2 cubed, we're doing 3 squared, sorry. We're plugging in our n, 3, into the derivative. To clarify, you plug in the number, and but again, we're plugging in the derivative. So let me do this slowly. I'm doing the third derivative right here, so I'm going to plug in 3. So negative 1 cubed, so I'll do this in this corner here. Negative 1 cubed times 3 squared over 3 factorial. I'm not plugging in 1. I'm plugging in the derivative number. Hopefully that makes sense. So it'll be negative over 3 squared, which is 9 over 6, because that's what 3 factorial is. So this is negative 3 halves. But again, this is just the derivative, so I still have to divide by the factorial, which I'm doing now. And then, again, most times you don't have to simplify, so I'm going to leave my answer like this. But sometimes you might need to simplify to make your the next part of the question a little bit easier. But this is how it works. Hopefully all of that made sense. Not my best explanation ever, but let me just recap it. You're given a derivative formula. Right when I see it, I'm given a derivative formula, whether I'm in the multiple choice or the free response questions. I'm expecting to create the factorial formula, to use the factorial formula to create my Taylor series, because I probably don't have a Taylor series already on the page. So third degree means up to the x cubed term. So here it was 3 terms by coincidence, but it's up to the x cubed terms and everything before it. So then what I do is I create the Taylor series formula. So this was just memorization. Derivative over factorial, x minus 1 to that number. And then for each term, after writing out the formula, I slowly plug in 1, 2, 3, whatever the derivative number is, to find the numerator of these coefficients into this formula. Hopefully that makes sense. No simplifying again, but for example, if we had to take a derivative, it might be nice to cancel out some numbers. I'm just going to take a derivative randomly, even though that wasn't the question, just to show you that it is easier to simplify. So like, for example, over here, this is all negative 1, so there'll just be negative 1 if you're taking the derivative. So this is the derivative. Like, for example, if you can cancel these out and notice that these are 1s, then it'd be easier to take this derivative, which is power rule. And then these 3, so again, it's just harder to take this derivative when the number looks like this. But if you want, we're dividing it, so it'll be 1 over 6. These will cancel. So I think this is negative 1/4. And then we do power rule. So it's 3 times x minus 1 squared. So again, simplification is sort of arbitrary, to be honest. But it makes your life easier if you have to take a derivative or an integral or even plug in. So hopefully that made sense. That's another key question. It's usually, so on these bricks, if it's an interval of convergence question, you probably do that in part A. And then if it's one of these factorial derivative questions, you'd probably do that in part A. That's why Taylor series bricks are so hard compared to other bricks, in my opinion, because they are very different. If you can sort of decide, this is the one where I do the factorial formula, and you do it correctly, then it makes it easier. But for example, in the next things we're going to talk about with the special functions, you don't do this at all. You don't use the derivative formula. You go from one Taylor series to the next. So I'm going to do that. We're going to write out some Taylor series. So you can practice this. Let's just do first four terms. So first four terms. Of something like, I don't know, x times sine of 3x. So you can try that. We're gonna try to build in difficulty. The ones you have to know are sine, cosine, and e. Potentially they would give you the ln one. So, but you can try to do it without it. So we're gonna write the first four terms of three Taylor series at this moment. We're gonna do ln of 1 plus 2x or something. And then we're going to write the Taylor series of this one in the last part, where there's two ways to do this, and I think there's definitely a better way. We're going to write out this one too. So you can try sort of writing these Taylor series. Again, unfortunately, it's really hard to get these questions right if you don't know your Taylor series memorized. You don't really have to memorize the general term. I think you can get away with that, but you do have to memorize like the first four terms, especially e, sine, and cosine. Again, most of the time they will give ln's and inverse tans, but you never know. But let's get started here. So sine 3x. So the first thing you do is you just write out the Taylor series for sine of x. So sine of x is the odd function, so it starts with x equals minus, and then it's all the alternating with all the odd ones. So it looks like this. And then I'm going to slowly find x times sine cubed, 3x. I don't know the best way to explain this, but to me it's obvious that you plug in 3x and then you multiply by x. Because I guess if you multiply by x and then plug in 3x, you're like really plugging into like this. You're plugging into this, and then you're plugging in 3x, which is not the same thing, if that makes sense. So hopefully it makes sense that you're going to plug in 3x first, and then you're going to do x. One thing I'm not doing at all, though, is I'm definitely not writing the factorial formula. I'm just going from one Taylor series to the next. And I like to do it in 2 steps. So I'm going to first find sine of 3x. Plugging in is way different than multiplying. When you plug in, you just replace every single x with 3x. But just keep in mind that when you're doing this, the 3x might be squared as well, or to some power. So when I place the first term, it will just be 3x, of course. But the next term, it'll be 3x cubed. Hopefully you see that. The next term would be 3x to the 5th. These numbers were too big because I really don't want to simplify this. Maybe I should try. 3 is a big number, though. I'm just going to use a calculator. I know that one, actually. But what's the 7th one? Okay. So yeah, I don't think you have to simplify, or if it would, the numbers would be way easier. But again, the 3 is being raised to the exponent. So it'll be, if you were to simplify, it'd be 3x minus 27x cubed over 3 factorial. At least trying to get rid of, showing myself that I know that the 3 is also being raised to the power. And then this 3 to the 7th is my favorite number in the world, 2187. But we're not done, but this part is easy. We just have to multiply everything by x. So just hopefully you see the difference between plugging in and multiplying. Here we plugged in, so we replaced all the x's with 3x. And for example, when we did exponent rules, we did the multiplication rule. And when we multiply everything by x, that's going to be distributing. So we're going to be doing the adding rule when you have like x's in the same base. So the final answer is going to be multiplying every single thing by x. We just bump every exponent by 1. So I'm just going to quickly do that. So notice anything that's not an x is not affected because we're not plugging in, we're multiplying. This should have x to the 5th, so it'll be x to the 6th. And so on. Not affecting the exponents, coefficients. Hopefully that makes sense. Pretty standard question. Okay, so just for space reasons, let's leave that we're going to do 2 over 1 plus x to the side. And let's do this ln of 1 plus x squared, 2x. So ln is the weird one. So again, it is more likely that if it were asked on the AP exam, for example, they would already give you the series. So the series is, not that I don't have these memorized, but it's x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4. And you can get it from integration, I think, as well as just doing Taylor series stuff. But again, it's just nice to have the formula already ready. So just be wary that when you have this formula, the 1 plus is like part of the formula. So if we're finding ln of 1 plus 2x, I'm not going to like plug in 1 plus into any of this. All I do is I just plug in 2x into all of this. And again, when you plug in 2x, it will be affecting the exponents. So it's 2x minus 2x squared over 2 plus 2x. And this one I'm definitely more likely to simplify because this one looks easier. So it's 2x, 4x squared, 8x cubed, and so on. Hopefully that makes sense. That one again is easier, but just be wary. Don't involve this 1 plus business at all. Just plug it in. Whatever you put right here is what you're going to plug into the function. Okay, last one is 2 over 1 plus x squared. There is ways to do this by memorizing the Taylor series for 1 over 1 minus x, but I like to do this by geometric series. So I like to think about this as a over 1 minus r. What's the a? Well, the a is going to be 2. And just keep in mind what's the r. It's not x squared, but because it's minus, it's going to be negative x squared will be the r. And then, so what I'm going to do is I'm going to take the a, which is the first number, which is 2, and I just keep multiplying by negative x squared to find the Taylor series. So it'll be a, just keep multiplying by negative x squared. And then because it's negative x squared, the next one will be positive. So, but the 2 is not getting affected because I'm only multiplying by negative x squared. So it'll be 2x to the 4th, 2x to the 6th, I think. Hopefully that makes sense. I don't know if anybody's still watching, but that's special Taylor series function stuff. That's, again, part A. So we've actually talked about most likely the part A of the 3 fricks. One of them is interval of convergence. One of them is they give you a derivative, so then you do the factorial formula. And then one of them is a special function frick like this, so you just start doing this sort of stuff, plugging in and multiplying. How much time have we done? Almost 40 minutes. We can do these small little questions here and there. I was going to do 2 quick multiple choice questions that some people struggle on, which is sort of the reverse. When they give you like a Taylor series, like 1 plus, let's just do 2 because it's the easiest number, plus 4 over 2 factorial plus 8 over 3 factorial. And they'll just say, what is the series? Or they'll just even write just equal, question mark. Or they can ask something like 1 minus 3 squared over 2 factorial plus 3 to the 4th over 4 factorial minus 3 to the 6th over 6 factorial. So sometimes they just say find the sum. So just be wary that I just want to stress this on the AP exam. Can we do one Lagrange? Yeah, we will. But I want to stress this on the AP exam. Anytime you see the words find the sum, there's a couple cases. The first case is that you're finding the sum between a finite number of stuff, like find the sum of the first 2 terms or something, find the sum of the first 3 terms, and that you would just literally add up the first 2 terms or the first 3 terms. But when you're finding the sum of an infinite series, this should sort of be your instinct. Because we don't really have many ways to sum infinite series. So the main way is geometric. So anytime I'm looking at the AP exam and I see find the sum, I'm thinking about geometric, a over 1 minus r. If the r is bigger than 1 in absolute value, then it diverges. So that's why the answer choice D would be chosen, because usually that's just diverge. But that's just one option. The second option is it could be a Taylor series. One of the special Taylor series, and that's what we're doing right now. So obviously it's going to be a Taylor series. But when we're doing this geometric one, how do you know which one it is? Like if you're taking a full AP exam, well, geometric won't have any factorials. Geometric means you're multiplying by the same thing every single time to get to the next term. That's what's called the ratio. And notice if we multiply here, one, you go 2. This one you actually, it's 1, right? Oh, it's 2 again. So you're not multiplying by the same thing every single time. So that's a dead giveaway that it's not geometric, and also the factorials is the super giveaway that it's Taylor series. So remember that in these questions, when it's Taylor series, all you have to do is identify the Taylor series and then just see what's getting plugged in. So it's really a 1-second question. It's actually easier right here because we still have the exponents. So notice if I replace all these 3's with x's, which I'm going to do right now, I just like try to identify what Taylor series this is, and this is one of the main 3 you should know. This is cosine. Because it's all the even ones, it's alternating. And when you have cosine, so now all we do is just see what number we plugged in. What number did we replace the 3 with? X. So the answer is cosine of 3. This question right here is basically the same thing, but we don't have the exponents. But notice that this is 2, this is 2 squared, this is 2 to the third. So it's going to be 2 is the number that's getting plugged in, like 3 was for this one. And then notice that this is not alternating, and it also is every single term, 1 factorial, 2 factorial, 3 factorial. So this is e to the x, so the answer is e squared. So there's no like work to be done here, if that makes sense. You just do this. Moving on. So it looks like we have to do a couple more things before we go. I want to take an integral of something of a Taylor series, and I also want to do some error bound and Lagrange stuff. So let's do that. So let's do the integral thing first. Integrals are not too bad, but one thing is that usually you have to find the Taylor series that you want to take the integral of first. So that would be the first part, or like it'd be part B, and then the integral would be in part C, for example. So like, for example, if we have this given right here, so we have this given, and we're trying to find the Taylor series, let's say third degree Taylor polynomial. For gx. So this is what we're trying to find. So again, when you're doing these questions, they usually break it up. You find f first and then you find g, because it's kind of hard to know what to do. And that's what we're going to do in this case. So first off, we're going to find the Taylor series for f. So that's not going to be the integral. That's going to be these derivatives. And again, hopefully you have an instinct on when to do the factorial formula and when not to. Here, if we're given a bunch of derivatives, or if we have the Fn formula, that is the derivative formula. So it looks like we will probably create a Taylor series from scratch using the factorial formula. So I'm going to do that. Anytime I do that, I like to write out the formula in general before I like to plug in numbers. This is Maclaurin because it's all about zeros. We can write Maclaurin. So it'll be f double prime 2 factorial x squared. And actually, if you can sort of foresee the future, we don't need this term right here, but just in case, I'm just going to write it. So this is the third term every single time when you're doing Taylor series. And now what I do is I replace the derivatives that they gave me. So I'm going to replace f of 0 with 1, f prime of 0 with 2. I'm just going to already simplify. 2 over 1 factorial. 1 factorial is 1, so it's just 2. And then when you plug in negative 2, 2 factorial again is 2, so negative 2 over 2 is minus 1. And then f triple prime is 4 over 3 factorial. 3 factorial is 6, so 4 over 6 will be 2/3. And while I did do that in simplifying plus plugging in one step, the reason why is I'm about to take an integral, and again, it's easier to take the integral if you simplify. So now I'm going to take the integral. So this again would be like part A of a question, and then part B is the actual integral. When I do this, I'm careful with the variables because it just makes it easier. So what you do is you plug in t for the variables, if you have write an integral sign, of course. So I just replace everything with t's. And then I just take the integral. And remember that what's nice about these Taylor series questions is that when you take a derivative or when you take an integral, it's always just power rule. So integral of 1 is t technically. Integral of 2t is t squared by the power rule. Then this one is 1/3 t cubed by the power rule. And then we get 2 What is this going to be? T to the fourth. So we're going to divide by 4. So that'll be t over 12, I think, which ends up being 1/6. That should be good. Okay. And I still have to plug in x and 0 because I'm still doing a definite integral here. So I plug in x. This is 1/6, by the way. When I plug in 0, this would go away because when you plug in 0, everything is 0. So I just have to do this. And just keep in mind that they would count off for this answer because we're trying to find the third degree, and that means up to the x cubed term. So you don't have to include this term. So this is the final answer. But again, this question is just made so much easier if you can just split up the question into 2 parts. First find f and then find g. G was actually more explainable in my opinion, just doing an integral with power series, whatever you got for f. F is a little bit harder, but the way we did it is we created the Taylor series and then we started plugging in the derivatives. And the reason why we're doing this is because we're given the derivatives. If we were already given f, or if f was like sine of x squared, we would have plugged in x squared into another Taylor series. But because they gave me the derivatives, I'm creating the first Taylor series. Hopefully that makes sense. But it's been 47 minutes, so I think to conclude, we're going to do everybody's favorite topic, which is error bound and Lagrange error bound. I'm not sure if I have great questions on this, to be honest. Let's do the... I kind of wanted like an easier question to start off. Yeah, how do they phrase these questions? Let me pull up some notes. Anybody have any questions though? Just everybody enjoying their whatever day it is today. What is this called? Miscellaneous. Okay, do I have a better question than this? Yes. So Lagrange is a little bit more rare than just standard Taylor series. So I'm going to do this question right here. Let's do this. So we have this Taylor series. So this is like the given. And usually error bound is the last question on a Taylor series frick, maybe second to last one. And the Taylor series goes, if you start plugging in numbers, they might give you this. It goes 1 minus x squared over 3. Let me find another term. If you plug in 2, it'd be plus x to the 4th over 5 minus x to the 6 over 7. So this is how the question would be presented. And then the question, so this would be usually a 2-parter actually. It's find the approximation of f of 0.5 or 1/2 using the second degree Taylor polynomial. So just keep in mind that as I'm about to do this question, this is not the error bound part. This is the approximation part, which some students confuse. The error bound part will be the next part, which is show that this approximation differs from the real thing. So differs from, let's say, f of 0.5. By, let's say, 1 over, if you have a bigger number in the denominator, that means you have a smaller fraction. I always have to think about that. Let's say 1 over 70. Okay, so again, this is how they present error bound questions, but just be careful. This is actually 2 questions. This is the error bound part. This would be like a subpart of the previous subpart. So find the approximation of f of 0.5. So f of 0.5 is impossible to find because it's a full Taylor series and we can't plug in 1/2 because it goes on forever. So what we do is we cut it off and we're going to use the second degree Taylor polynomial to find the approximation of that. And so what we're going to do is we're going to take 0.5 or 1/2 and we're going to plug it into this function. But we only have to plug it into specific terms. Keep in mind that it's not the first two terms. It's not just the x squared term, it's up to the x squared term, which does happen to be the first few terms. But second degree telepolynomial is this, fourth degree would be this, sixth degree would be this, and so on. So I'm going to do the second degree, so I'm covering this up, and I'm going to plug in 0.5. I like to work with fractions, so I'm going to plug in 1/2 instead. And unfortunately, on the AP exam, this is not calculated because it's always the last frick. So I'm going to slowly calculate this. 1/2 squared is 1/4. Divided by 3 is 1/12. Just keep in mind that when you're like dividing fractions, 1/4 over 3 is not 1/4, is not 3 over 4. It's 1/4 times 1/3, so it's 1/12. And you get 11/12. So again, this would be the answer to like the previous subpart. And now we're going to do the actual error bound part right now. So the error bound formula is S minus Sn is less than Bn plus 1. So let's talk about what this means for this context of this question. S is the impossible thing, the sum of infinite things. So that's f of 0.5. I don't know if they would count off if you didn't like write what each of these things are, because S minus Sn less than Bn plus 1 has no meaning if you sort of don't have any values to it. But Sn will be the T2, meaning that we plugged in 0.5 into the second degree telepolynomial. It is this approximation, so it's 11/12 actually, so you could have written that instead. And then we want to plug it into the next one over, and so the next one over is going to be B3. So again, impossible thing, approximation, which is 11/12, error bound. So when you're doing the error bound, you're actually finding this number right here. You're not really finding anything on the before this. Keep in mind that what this is trying to say is that this is impossible. 11/12 is an approximation for this impossible thing, and how good is it? It's a pretty good approximation. It's within 1/70th, which is a pretty small number. So what you do is you just look at the next one over. So because we use these two terms for the approximation, the next one over is this term right here. I'm going to circle all of this because if it were a minus, we would not include the minus because of the absolute value. Some students struggle with that. So this is the next term over, x to the 4th over 5, and you're not going to have any x's. You need to replace it with a number. And what number do you replace it with? You're going to replace it with 1/2 because we're going to plug in 0.5 into the entire frick. So you plug in 1/2. And you just simplify as best as possible this number. 2 to the 4th is 16. And then again, when you divide this, just be careful. This is not 5/16. This is 1/16 times 1/5. So this is 1/80th, which is less than 1/70th. So this is probably, if you want to work on your error bound questions, this is probably the most classic example of an error bound question. Where sometimes they'll ask you to find the approximation on a previous part, but sometimes they won't. All you do is just look at the next term over and just plug in your number. That's really all you do. It's just the wording is kind of confusing, so some students struggle with it. Hopefully that makes sense. Last question we're going to do is a Lagrange error bound. So let's do that. And sometimes these Lagrange error bounds have like pretty long wording. So let's say we have like Pn is our normal Taylor series polynomial of degree n. And then what are we working with? They give you this sort of like bound for the derivatives. So again, anytime I like see this like derivative thing, I'm like, oh, this is the factorial formula probably. And then they want you to show that this is true using Lagrange error bound. Minus P4, 1. So this is actually 1 from my notes, but I think it's 1. And we want to find the smallest number, so the smallest error bound possible by Lagrange. All right, so this is the question. Again, if you were doing it from error bound, this is the impossible thing, this is the approximation, and we're trying to find some error bound. So when you're doing Lagrange, the way it works is it works like Taylor series. So because we're doing P4, it's the next one over, just like with the error bound. So it's the fifth one. So we're going to write the fifth one. We'll write m first because that's how they usually write it. But it's divided by 5 factorial x to the 5th. This Taylor series, by the way, is around x equals 0. It's a Maclaurin series. So again, this is the Taylor series formula every single time. X to the fifth, 5 factorial. And what m is m is the bound of the fifth derivative. So m is the bound for f5. I think it will say Lagrange in these questions, but again, how I know it's Lagrange, I don't know what your name is, Alia Shapiro, but if you're given like this derivative thing, you know it's Lagrange. But if you're not given this derivative thing, it's probably not Lagrange. So like, if in this question right here, because I was given a Taylor series, it said like find the approximation, and there was nothing about a derivative formula, so I knew it wasn't Lagrange. But this one I do know it's Lagrange because they give me this derivative formula. And sometimes like in crazier fricks, it's like a graph of this derivative. But again, like somewhere on the page will be this derivative thing. And so that's why you know like, oh, this is Lagrange as opposed to regular error bound. So fifth derivative. So what's the m in this case? All we're going to do is we just plug in 5 into this formula. So if we plug in 5, notice that this will be, hopefully I'm not running off the top of the edge of the page, but it's 5 over 5 plus 2, which is 5 over 7. And then all you do is just take this number and replace it with m. The 5 factorial is just always there. So it's still there. And then you still have to plug in a number for x, but luckily it'll be 1. But if it was a harder question, like it was 2, 1/2, you would have to plug in that number. And then you just simplify this number, and then this is the answer. Usually this is a multiple choice question, where the k will be the final answer. So let's simplify. 1 to anything is 1. 5 over 7. Again, you like flip this fraction is what some people say. So it's 1 over 5 factorial. And then if you do this math, you can go crazy. Like 5 and 5 factorial will cancel, so you'll be left with 4 factorial. But if you want, it's just 5 and 120. So it's 1 over 24. You still have the 1/7. So this final answer is, I don't know. I'm going to type this in a calculator before. It's 168. So this is the answer. Hopefully that makes sense. And we got done with a couple minutes to spare. I just really want to stress that there's 3 types of Taylor series questions. The first one is you're trying to find interval convergence for part A. Usually they give you a general term and you set up the ratio tests and then you do all the magic. One of the derivative, the second, so that's the first one. The second one is when they give you a derivative formula. Let me see if I have a sort of got confusing on my pages. Let's see, that's interval right here. So if they give you a derivative formula, Fn, this is upside down. Where is it? This one, maybe? I thought I had a sheet though, like we did those. Oh yeah, right here. You're given a derivative formula. That's going to be a Taylor series frick when you do the factorials. So again, first one is interval convergence. Second one is derivative formula. And then the third type is when they give you one of the special functions like sine or cosine or ln. And for those, you should know that you would not do the factorial formula. You'll probably just plug in and multiply. That's the part A for all these fricks. Then part B and C can really be any game, but usually it's maybe plug in some more, or it might be take a derivative. It might be, this is sort of multiple choice or not this. It might be take an integral. And then it might be error bound. Error bound appears a lot in all these fricks. Where is error bound? So this standard error bound, remember this was like a 2-part question even. So as you're doing these Taylor series fricks, just as a recap, part A will either be interval of convergence, or using the factorial formula to create the Taylor series, or using a special function to create the second Taylor series. So that'd be part A. And then part B could be taking a derivative, taking an integral, plugging in some stuff maybe, or doing error bound. Hopefully that makes sense. Does anybody have any questions? I feel like we got a lot done actually. And then I only messed up -5 times. So diverge or converge. Bracket is converge, and then parentheses is diverge when you're doing interval of convergence. But hopefully that makes sense. Hopefully everybody enjoys their President's Day, if that's a thing. But thanks for watching, and we'll be back. I think we'll probably do area and volume for AB at some point this week. Maybe derivative topics for pre-BC, maybe. But Taylor series is the big gun. So hopefully this was useful. Thanks for watching.